Hello, my name is Anton, and I'm going to present you our new online capable polytope vertex search algorithm. This paper has been co-directed by my thesis supervisors Vincent Padois and David Danet. Traditional industrial robots and their environment are optimized for a set of specific long-term tasks, and when it comes to collaborative robots, this is no longer the case. To share the environment with humans, they need to be adaptable to unexpected events. Their tasks become much more flexible and harder to plan in advance, and the human proximity involves a lot of safety risks. Therefore, evaluating robots' capabilities and optimizing their performance in advance with tools designed for more traditional robots is no longer a suitable approach. New online metrics are needed to allow for safe and responsive robots. One of the most well-known robot capacity metrics is force capability, robots' ability to resist and apply forces in arbitrary directions. The most widely used force capacity metrics are manipulability ellipsoids. They are very efficient to calculate, but they are just an approximation of robots' true capacities. Robots' true capacity has a shape of polytope. Polytopes have many advantages over ellipsoids. They can integrate robot dynamics, they can account for external forces such as gravity, and in the context of collaborative robotics, they can be used to calculate the common force capability of multiple robotic systems. However, evaluating polytopes relies on the vertex enumeration problem, which is computationally intensive, and it is the main obstacle for wider use of these algorithms in practice. In this paper, therefore, we propose a new polytope vertex search algorithm for force polytope calculation. This algorithm directly exploits the geometrical structure of the problem and considerably improves the computation efficiency. With the execution time of just few milliseconds for standard manipulators, it is suitable for real-time use, and it opens many possibilities for applications in robot control and collaboration scenarios. As the visual aid to this algorithm explanation, we'll be using a 3 degrees of freedom planar robot. This robot has 3 joints, and each of the joints can apply joint torques, and each of the joint torques is limited in between some minimal and maximum value. If a certain 2D Cartesian force is applied to the robot's end effector, the robot can counteract it by applying appropriate joint torque vector. But since the joint torques are limited, the range of Cartesian forces that the robot can counteract is limited too. And this range of rejectable Cartesian forces represents its force polytope. The achievable set of joint torques can be represented as a hypercube or hyperrectangle with side lengths equal to the ranges of each of the joint torques, from minimal to maximum value. In the Cartesian space, this hypercube is mapped to a convex polytope of achievable Cartesian forces. In this example, it's a 2D polygon. The dual relationship between joint torques and the Cartesian forces is defined through the Jacobian transpose matrix. And we also know that only the joint torques belonging to the image of the Jacobian transpose matrix can generate the Cartesian force, here shown in blue, inside of the hypercube. Finally, the vertices of the intersection of the hypercube and the image of the Jacobian transpose matrix can be directly mapped to the vertices of the force polytope. And our algorithm exploits this fact. First, we find the vertices of the intersection by efficiently navigating the hypercube faces, and then we project them to the Cartesian space using pseudo-inverse of the Jacobian transpose matrix. To navigate the hypercube faces, we first transform the joint torque vector tau to linear combination form. This is done by defining a new set of base vectors and using the scalars alpha, bounded in between 0 and 1. Then we leverage this new representation to intuitively build a set of linear systems for each of the hypercube faces. In the case of 3 degrees of freedom robot, we will be fixing 2 out of 3 scalars alpha to either 0 and 1 and solve this linear system. If the remaining scalar alpha respects the vertex condition, the force F is the vertex of the polytope. If not, this hypercube face doesn't have a vertex. For a generic robot with n degrees of freedom and m Cartesian forces, the proposed algorithm in the worst case resolves n-m out of n linear systems, and for each one it calculates 2 on the power of m vertex conditions. The in-depth analysis of this algorithm and the comparison to the state-of-the-art methods can be found in the paper. To put these results in context, the algorithm was tested on 7 degrees of freedom robot Franka Emika Panda and 6 degrees of freedom robot UR5. For Panda robot, the algorithm on average calculates 8 matrix inversions with average execution time of 3 milliseconds. For a bit simpler UR5 robot, these values are even lower, and the average execution time is 1.5 milliseconds. All the results were averaged over 1000 random robot configurations, and the algorithm was implemented in programming language Python. To demonstrate the potential of this algorithm for robot control, we created a simple example experiment. In this experiment, 2 Panda robots are jointly carrying 12 kg object. Each of the robots compensates for a part of the total mass as a function of their own maximum carrying capacity. The human operator freely moves the object through the common workspace. In the bottom left, we show each robot's carrying capacity as a vertical line, blue line for robot 1 and green for robot 2. The black points on the capacity lines represent naive strategy with equal mass distribution. And the white points show the proposed adaptive strategy that leverages online capacity calculation. And any point that exceeds robot's capacity will be shown in red. The 2 top graphs on the right show each robot's carrying capacity, force applied by the proposed strategy, and in black dashed lines the equal mass distribution strategy. The graph beneath shows the sum of the maximum carrying capacity of the both robots and sum of their forces applied. And in the bottom graph, the evolution of the carrying ratio is shown. As the operator moves the object towards the table on the right, robot 1's carrying capacity drops significantly, and it is no longer able to carry half of the object's weight. The proposed strategy accounts for this, and on the bottom graph we can see that robot 2 now carries more than 70% of object's weight. Towards the end of the experiment, robot 2 has much lower carrying capacity than robot 1, and in this case robot 1 carries almost 80% of object weight. In this experiment, we showed that any constant strategy would lead to failure even though carrying capacity of the 2 robots exceeds object's weight during the whole time of the experiment. Force polytopes allow for calculation of the exact force capacity of multiple robotic systems as well. One typical scenario is when multiple robots apply forces in the same direction. Then their contributions are summed, and their common capacity can be calculated as a Minkowski sum of their polytopes. The other typical scenario is if the robots apply forces that exactly cancel each other. Then their force capacity is defined as the intersection of their polytopes. Both Minkowski sum and intersection can be calculated in real time using our algorithm. In this video from the previous experiment, each robot's separate polytopes are shown down in left, in green and blue, and on the right side we show 2 collaborative scenarios, Minkowski sum and intersection. In this paper, we presented a new efficient algorithm for force polytope evaluation, which considerably reduces the computation time. This algorithm can be used for online robot control, as it was demonstrated in a collaborative carrying experiment. It has the great potential to be used for evaluating common force capabilities of multiple robotic systems, and as the future work, we plan to extend it to human-robot collaboration. You can find our contact details and link to the GitHub repository in the bottom of the slide. Thank you very much for your attention.